Hello, we're back again. And what's the solution? Well, chemistry is the solution. Today we're talking about some solutions and dilutions. So as we start talking about solutions, we're talking about when we dissolve something usually in water. And that involves solubility. You guys have heard this word before, kind of quizzed you on it all year long. And solubility is just the ability to dissolve a solute. And remember that a solute is the stuff that we're dissolving. Solvent is like the water or the oil or something that is doing the dissolving. So not everything is dissolved in water. Some things are dissolved in oil, some things get dissolved in gasoline, some things get dissolved in alcohol, but for the most part we're usually talking about water. And that's where our solubility rules can help us. Remember, the solubility rules, or on your purple sheet, can tell you what things will dissolve in water and what things usually won't. Obviously, it doesn't contain everything on there. Rocks are not on there, and most rocks don't dissolve in water very easily. But remember that rocks are made up of chemicals. So if we break down all those chemicals, most of those individual chemicals are on that sheet. When we're talking about solubility, something that you haven't seen yet is that sometimes we express it in the grams of solute, or the grams of what we are dissolving, per 100 grams of solvent. So essentially, if we can only dissolve 2 grams of solute in 100 grams of solvent or 100 grams of water, it's not very soluble. That means not a whole lot is dissolving. But if we can dissolve 200 grams of something in 100 grams of water, that would be very soluble. That means that a ton of it will continue to dissolve. And we're going to kind of look at how that solubility is affected with some different factors. So there's 3 main factors that we look at here. The first one is how the solvent and the solute interact together. Remember that polar things usually dissolve polar, and nonpolar things usually dissolve nonpolar things. So we use that rule of like dissolves like. Obviously, we're probably never going to get oil, pure oil and water to mix and dissolve in each other because they're 2 unlike substances. We can also use then, again, the solubility rules. Solubility rules kind of help us determine how those interactions are going to occur, what's going to happen when those substances come together. Now the next factor is temperature. And hopefully you've noticed this some point throughout your life, that as temperature rises, most solids and liquids will increase in their solubility. Okay, if you think about tea, if you're trying to dissolve sugar into your iced tea, you got to stir quite a bit to get it to dissolve. But if you try and put sugar into your hot tea, you pour it in, stir it up, and it's gone. As temperature rises or as the temperature increases, your solids and liquids will tend to dissolve more. The opposite is true for gases. Gases are already moving around so fast that when you put them into a liquid and increase the temperature, they move around so fast out, and their solubility actually decreases. So gases and solids and liquids are a little bit different from each other. Solids and liquids increase solubility with temperature. Gases are going to decrease. Pressure also has a little bit to do with it. If you think about solids and liquids, they're kind of already smushed together for the most part. Pressure really doesn't affect them. But as pressure increases for gases, we can put so much pressure on top of a solution that the gas has to go in. This happens a lot in your soda. When you open a soda, or if you know inside your soda, there's a bunch of gas bubbles. And you can kind of, you know that they're there because if you shake up the soda and open the cap, it all comes out. But inside the soda, there's tons of pressure. All that pressure is keeping the gas in your drink. Okay, so that's all the carbonation that's there. As soon as you open the cap and release the pressure, all the bubbles come out. So as we're talking about types of solution, we talked about how we could get more stuff to dissolve. But there's also different types of solution. Unsaturated, saturated, and supersaturated. This is the fun one, by the way. So unsaturated solutions have less solute than it can really dissolve. That means that you can always put more in. So this would be like if I were to dissolve 1 gram of sugar into water. That would be an unsaturated solution, and I could test that by putting more sugar in. As long as stuff keeps dissolving, that means it's an unsaturated solution. A saturated solution contains the absolute maximum amount of solute that it can. So that means I'm going to keep putting in sugar, keep putting in sugar. At some point, it's going to stop dissolving. And that point right before it stops dissolving is where it's saturated. That liquid has as many sugar molecules as it can in that liquid. And a supersaturated one is kind of a weird deal. It actually contains more solute than can theoretically be held. And this kind of happens in some unique situations. We'll talk about that a little more. You can graph this type of solubility, unsaturated, saturated, and supersaturated, pretty easily. So we have our grams of solute. So we usually do grams of solvent per 100 grams of water. So here's our 100 grams of water, and this line is going to tell us how many grams of solute. So for Ki here, in 100 grams of water at 0 degrees Celsius, we can put 130 grams of Ki in 100 grams of water. Notice that as the temperature increases, we can fit more in. So this is at 0, but at 25 degrees, we can fit 150 grams in. Okay, so remember, solids and liquids will increase in solubility as the temperature increases. This one, if you notice, decreases as the temperature increases. Ammonia. So that one probably tells us that it's a gas, because we know that solubility decreases for gases. Now above this line is where we can't fit anymore. This would be supersaturated. So if we somehow got 150 grams to fit into 100 grams of water at 0 degrees, it would be a supersaturated solution. If we have 130 grams in our water at 0 degrees Celsius, this is a saturated solution. Anything below that would be an unsaturated solution. That means we can still fit more in. So that supersaturation, I told you it's kind of weird. And this occurs when something saturated cools down. We know that solubility increases as the temperature increases. So the solubility is going to decrease as the temperature decreases. But something kind of cool happens. And as all of these molecules in here are cooling down, they're starting to pack together, they don't always just come and form a solid. Sometimes they form this equilibrium where stuff is kind of moving in and out and nothing really happens until you disturb it. So in this one right here, this is a solution that has a ton of this solute dissolved into the solvent. We've let it cool down and we've added a disturbance. We put one crystal of this salt in here and it crystallized all out. In this video, you notice that as this man starts what he's doing, the stuff in the solution is clear, and then as he pours it out, it disturbs it, and it comes out as a solid. So any disturbance can make it crystallize out. And we'll kind of see this in a lab we do later this week. All right, so we've talked about putting stuff into those solutions, but sometimes you have to dilute it. Okay, so if we have a solution and we've put all this stuff in it, we then add more water, there's still the same amount of solute in there. We have just lowered the concentration because we've increased the volume. Okay, so dilution consists of adding more solvent or more liquid to a solution so that the concentration goes down. The total number of solutes is the same. Okay, so if you think about this solution up here, there's 12 little dots. If we add water to it, there's still 12 little dots. It's just in a bigger volume. So if we have 2 moles per liter compared to 2 moles per 2 liters, this would give us a 2 molarity, this would give us a 1 molarity. So that volume does affect how concentrated it is. We haven't been changing the concentration as much, we've been changing the amount of solute. But now if we start looking at changing this volume, it does dilute it. Okay, so we could get a lower molarity. Sometimes you'll see this in parts per million, milligrams per liter, sometimes percent concentration. Most of the time, we're going to be looking at molarity. Now we can figure out what the new molarity is going to be very easily with this cool little formula. And it's simplified by using the first molarity times the first volume is equal to the second molarity times the second volume. So as long as we know 3 of these variables, we can solve for another. So if we want to know what the molarity is going to be, if we have a solution and we dilute it to twice the volume, we can find out what the new molarity is going to be. So let's practice that for a second. In this one, we have 1 liter of a 0.25 molar solution. So that tells us that our first volume is 1, and our first molarity, before we change it, is 0.125. Now it tells us we want to dilute the solution to 0.05 molar. So how much water should we add? Well, we know that now our second molarity has to be 0.05, so we need to know what our new volume is going to be. Remember that V1 M1 is equal to V2 M2. So if we plug this into our formula, we have 1 times 0.125 is equal to our unknown times 0.05. So in order to solve for our V2, all we have to do is divide by 0.05 each side. So if we then take 0.125 divided by 0.05, we would get a V2, or a final volume, of 2.5. Now this doesn't tell us how much water we should add. This tells us what our final volume should be. So if we started with 1 volume, our V1 is 1 liter, we have to end with 2.5 liters, then that means 1.5 liters is how much we have to add. Okay, so it's a pretty easy formula. M1, V1, M2, V2. Plug them in, chug it out. If you have any questions, again, feel free to come ask. Otherwise, we'll be working with this a little bit more in class. We will talk to you later. Peace out. Goodbye. Farewell.